One of them was Sir Frederick William Herschel, born in 1738 in Hanover, Germany. Herschel became well known as both an astronomer and as a musician. He moved to England in 1757. Herschel is famous for his discovery of the planet Uranus in 1781, the first new planet discovered in the modern era. But Herschel made another dramatic discovery in 1800. He wanted to know how much heat passed through the different colored filters he used to observe sunlight. He noted that filters of different colors seemed to pass different amounts of heat. Herschel thought that the colors themselves might be of varying temperatures, so he devised a clever experiment to investigate his hypothesis. He directed sunlight through a glass prism to create a spectrum, and then measured the temperature of each color. Herschel used 3 thermometers with blackened bulbs for each color of the spectrum. As he measured the individual temperatures of the violet, blue, green, yellow, orange, and red light, he noticed that all the colors had temperatures higher than the controls. Moreover, he found that the temperatures of the colors increased from the violet to the red part of the spectrum. After noticing this pattern, Herschel decided to measure the temperature just beyond the red portion of the spectrum in a region where no sunlight was visible. To his surprise, he found that this region had the highest temperature of all. Herschel's experiment was important because it marked the first time that someone demonstrated that there were types of light that we can't see with our eyes. What Herschel had discovered was a form of light beyond red light, now known as infrared radiation. Our eyes are detectors that are designed to detect visible light. There are other forms of light that we can't see, as Herschel had discovered. Few animals can see infrared. However, rattlesnakes and other pit vipers have 2 small organs or pits between their eyes and nostrils that detect infrared radiation. Hence, even in the dark, they can accurately strike at warm-blooded prey. The human eye can only see a very small part of the electromagnetic spectrum. At one end of the spectrum, we cannot see gamma rays, ultraviolet light, and X-rays. While at the other end, our eyes cannot see infrared, microwaves, or radio waves. Infrared radiation lies between the visible and microwave portions of the electromagnetic spectrum. The difference between infrared and visible light is the wavelength. Infrared has a longer wavelength than what we can see with our eyes. We can illustrate this in another way too, using Max Planck's law of radiation, formulated in 1900. It's an equation that produces a curve which illustrates that the warmer a body is, the greater its emission at each wavelength, and the shorter the wavelength at which emissions peak. It seems complicated, but it isn't. This is the curve at 37 degrees Celsius, the normal body temperature of a human being. Maximum radiation is emitted at about 9.3 micrometers, and we can only see this radiation with an infrared camera. If the temperature rises to, let's say, 300 degrees Celsius, the temperature of a soldering iron, the peak of radiation moves to about 5 micrometers. We still need an infrared camera to see this. Suppose the temperature rises to 5,500 degrees Celsius, the temperature of the sun. Then the peak of radiation is 0.5 micrometers. And this is right in the part of the spectrum that we can see with our eyes. The primary source of infrared radiation is heat, or thermal radiation. Any object that has a temperature above absolute zero emits radiation in the infrared region. Even objects that we think of as being very cold, such as ice cubes, emit infrared radiation. We experience infrared radiation every day. The heat we feel from sunlight, a fire, or a radiator is infrared. And although our eyes can't see it, the nerves in our skin can feel it as heat. The warmer the object, the more infrared radiation it emits. An infrared camera, also called a thermal imaging camera, will measure the amount of infrared radiation falling on its detector. Based on the differences in radiation, thermal imaging cameras can produce a clear thermal image even in total darkness. Thermal imaging is not the same as using night vision goggles. No, night vision goggles amplify small amounts of visible light so that objects can be seen at night. They only work if at least some light, like moonlight or starlight, is present. Thermal imaging works by detecting the heat energy being radiated and needs no light at all. FLIR Systems, the world leader for thermal imaging cameras, develops and markets the most sophisticated thermal imaging cameras, both with cooled and non-cooled detectors. Cooled detectors operate in the 2 to 5 micrometer waveband. They contain a cryocooler and are able to detect the smallest details at ranges up to over 20 kilometers. Cameras with cooled detectors like the FLIR Systems HRC can also be equipped with a continuous zoom on the infrared range. Uncooled detectors operate in the 8 to 12 micrometer waveband. Most FLIR Systems thermal imaging cameras contain an uncooled vanadium oxide microbolometer detector. Contrary to cooled detectors, they contain no moving parts, which reduces downtime and maintenance. They're less expensive, but do not have the range performance of a cooled detector. But how does an infrared camera work? Although an infrared camera looks a lot like a normal video camera, it's far from the same thing. Glass does not transmit infrared radiation well, and so the lenses of an IR camera are made of germanium. This expensive metal is a good transmitter of infrared radiation. Infrared energy coming from an object is focused by the optics onto an infrared detector. The detector sends the information to sensor electronics to process the image. The electronics translate the data coming from the detector into an image that can be viewed in the viewfinder or on a standard video monitor or LCD screen. Thermal imaging cameras have found their way into many useful applications. Thermal cameras, which are engineered and designed by FLIR Systems, are based on the most advanced technology, both in terms of hardware and software, and have contributed to the positioning of FLIR Systems as the world leader for thermal imaging cameras. Security and surveillance professionals are benefiting from the power of thermal imaging cameras. It helps them spot intruders in total darkness, in all weather conditions, even at extremely long ranges. The automotive sector has discovered the benefits of thermal imaging for driver vision enhancement. Thermal imaging cameras can see up to 5 times further than headlights and can help to avoid accidents. Thermal imaging cameras are today already sold as an option on selected BMW 5, 6 and 7 models. In maritime environments, thermal imaging can help captains to navigate in the darkest of nights. Thermal imaging can pick up small objects that are not detected by radar but can damage a vessel severely. In firefighting, thermal imaging cameras can save lives by locating people caught in heavy smoke. Installed in aeroplanes, thermal imaging can help pilots by enhancing the ability to see terrain and other aircraft. Installed in unmanned aerial vehicles called UAVs, thermal imaging allows the aircraft to fly in total darkness and detect targets through smoke. Thermal imaging can detect and follow vessels that are illegally polluting our seas. And there are numerous other, sometimes life-saving applications for thermal imaging. It's thanks to William Herschell's amazing discovery and the never-ending commitment of FLIR Systems to develop the best thermal imaging cameras on the market that we're able to see things in a different light.